Not since the time of the Model T and Henry Ford has so much change and excitement engulfed the automobile industry. New technologies, new values, some of which have resulted in new regulations, and the prospect of 2 billion vehicles on the road by mid-century have all conspired to dramatically alter a device that, for most of us, is more than one of utility. In this set of videos, we're going to talk about the reasons behind or the motivation for vehicle electrification, for making these dramatic changes to vehicles. And we'll delve more deeply into the device which many see as the linchpin behind the successful introduction of ZEVs, zero emissions vehicles. That device is the battery. So it's probably not much of a surprise to hear that the transportation sector has a huge impact on petroleum consumption and CO2 emissions. Here in the US, the transportation sector accounts for about 2/3 of the petroleum used. And with all of that petroleum being combusted in vehicles, it's also probably not a surprise to hear that the transportation sector is responsible for the largest share of CO2 emissions of any end-use sector. In fact, the only sector that releases more CO2 is the power generation sector. So you take those two data points and then you think about, well, the growing population of the world, economic growth in Asia, and there have been projections that say that in the next, in the 50-year span between 2000 and 2050, we should expect to see a tripling in the number of vehicles on the road globally. So over 2 billion vehicles are expected. So those are some pretty scary scenarios, and the question we're going to address is, what benefit can be expected from electric vehicles? Can they help reduce the environmental impact of the vehicle on our Earth? Or, on the other hand, are we simply displacing emissions from, say, the back of this vehicle to someone else's backyard, where we're producing the electricity that feeds the battery that propels this vehicle? I'm driving a Chevy Volt, which is what's called a plug-in hybrid electric vehicle. I consider it to be a marvel of modern technology because it can travel about 35 miles on battery power alone, and those batteries are built on a lithium-ion chemistry that contain about 16 kilowatt hours of energy. So after those 35 miles of electric motor expired, what the Volt does, which is quite smart, is switch over to the use of an internal combustion engine, which in a range extending mode provides about another 300 miles of driving range. So when you factor in battery operation and the internal combustion together, the EPA tells us we're getting about 93 miles per gallon in this vehicle, which is really phenomenal. What I'm about to do may seem a little unusual, but if you were around a century ago, in the early 1900s, you would have seen several people plugging in their electric vehicles, especially in New York City, where taxis that were based on batteries were fairly common. In fact, there were charging stations every few blocks in New York City, and the wife of Henry Ford, Clara, owned her own electric vehicle that was manufactured by the Detroit Electric Company. So back in those days, the internal combustion engine was in a fairly early stage of development. For example, one had to turn a crank to get those vehicles started. And electric vehicles were actually quite a bit more convenient. They were more reliable, and so they were fairly popular back in those times. So now flash forward about 100 years, and it's clear to all of us that the internal combustion engine has recaptured the title of king of the road. Now, one of the questions we're going to discuss is whether it's time for a renaissance in electric vehicles. What's the rationale for electric vehicles? If we're going to devote a lot of effort to developing new batteries and new technologies, it should be pretty clear that there's going to be some benefit to society. For example, reduced CO2 emissions or less reliance on fossil fuels. To help us answer that question, we're going to talk about something called a well-to-wheels analysis. And part of that analysis is understanding how far people typically drive and how big the battery ought to be to capture some fraction of those vehicle miles traveled. In addition to that, batteries are big, heavy, and expensive. So we almost end up with a Goldilocks scenario where if I travel, say, just a few miles every day, but I'm forced to buy a car which has a very large battery, I'm paying for something I may not use very much. And to give you one example, the Chevy Volt we have here, the battery in this car is on the order of about 400 pounds, and the Department of Energy has estimated that it costs about $10,000. On the other hand, if the battery is too small, well, then the number of miles traveled using that battery will also be small, and the benefits we would expect to accrue could also be rather minimal. In front of you, you'll see a plot which illustrates the fraction of vehicle miles traveled on a given day as a function of what's on the x-axis, which is the all-electric range, for example, the 35 miles we talked about, which the battery is capable of in the Chevy Volt. So for example, in the Volt, if we can travel 35 miles, what this plot shows is that you can capture about 55 to 60% of vehicle miles traveled just on the battery alone. That's pretty good. The other thing you'll notice is that as we go to farther points in this curve, the curve starts to flatten out, and there's a significant fraction of vehicle miles, on the order of about 15%, which occur for trips that are larger than 100 miles. That's pretty significant and results in what's called range anxiety. And to give you another example, if I were to take my family from Ann Arbor down to the Toledo Zoo for the weekend, that's about an 80-mile trip. And so if I were driving something like a pure electric vehicle that only got an 80-mile range, I would just be getting back to Ann Arbor in time for the battery to be depleted. So that's one reason why something like the plug-in hybrid vehicle, the Chevy Volt, is a good idea, because it alleviates that range anxiety. And the other alternative, as you can see, if we do move to purely electric vehicles, people might have to have, say, one electric vehicle they use for their daily commute, but then on the weekend or during holidays when they want to visit grandma, they'd switch over to their internal combustion engine where they could travel 300 or 400 miles on a single tank of gas. Okay, so let's assume we've got a plug-in hybrid electric vehicle and it can go about 40 miles on battery charge alone. The question we now want to ask is, what sort of benefit can we expect? And that's where a well-to-wheels analysis comes into play. This analysis allows us to compare various different fuels, various different vehicle technologies, and determine, where are the trade-offs, what sort of technology is best in terms of CO2 emissions, in terms of efficiency, in terms of cost, in terms of petroleum reduction. So it's a multi-dimensional analysis, and it's not a straightforward thing to do, especially when we start to consider heavily electrified vehicles. Well, in this case, we're starting to couple the vehicle to the electricity grid. And so to do the analysis correctly, we have to go back to the beginning and ask the question, well, how is this electricity produced? Is it produced from the combustion of coal? Is it produced from the combustion of natural gas? Maybe renewables are used. All of these factors, including, for example, the time of day, even the season during which that electricity is produced, can have some effect upon the efficiency, upon the CO2 emissions of an electric vehicle. Argonne National Labs has done a very nice analysis to look at the well-to-wheels efficiencies, performance of various fuels and vehicle technologies. And this plot summarizes how plug-in hybrid vehicles stack up compared to other vehicles you might find on the road today. So on the x-axis you see the amount of petroleum which is consumed by a given vehicle, and the different symbols represent this different combination of vehicle fuel types. On the y-axis, you'll see the amount of greenhouse gases that are emitted. So the nice way that this plot has been normalized is to take the value of a conventional gasoline vehicle and assign that a value of 1. So below and to the left of that value of 1 and 1, any dot you see which falls within that box indicates a technology which has the potential to improve upon what we can expect from a conventional gasoline vehicle. You'll also notice that there's several different colors associated with these plots, these different points in the plot. And I just want to go through a couple of them because this is rather complicated. For example, pink represents gasoline, brown represents diesel. The other most important point is the meaning of the shapes of the symbols. For example, when we're talking about plug-in hybrids, we're going to be pulling electricity from potentially different parts of the country which use different generation mixes in the production of that electricity. So for example, you'll see a rectangle. That represents the average mix of electricity on the US grid. A circle, on the other hand, represents the sort of electricity you'd expect to find in Illinois. And in Illinois, we know there's a lot of coal used to produce electricity. On the other extreme would be California, which is represented by a triangle. Most of the electricity in California is generated by natural gas. And at the far end of the spectrum, you would see a square which represents electricity which is produced from 100% renewable. So for example, wind or solar. So on top of that, we've superimposed the performance of plug-in hybrid electric vehicles depending on whether they travel, say, 10 or 40 miles. So the small circles represent a 10-mile range only on the battery. 40 miles is represented by the bigger symbol, and you'll see a line which connects those two. Finally, the last point of reference is what happens with a conventional hybrid electric vehicle, and that's represented by an asterisk. So for example, you'll see a pink asterisk which represents the performance of something like the Toyota Prius. And in this case, we're getting about maybe a 30% improvement both in petroleum consumption and in greenhouse gas emissions. That's pretty good. So let's simplify matters a little bit by just looking at how the petroleum fuels perform in the context of a plug-in hybrid vehicle. So if you look at petroleum use, so again we're looking at the x-axis, and we ask the question, how much better can we do than a conventional gasoline vehicle? You'll see that basically all the plug-ins that travel 40 miles range, we reduce the petroleum consumption by about 60% compared to a gasoline vehicle. That's pretty good. However, there is one exception, and that occurs in the case of New York State. And the problem there is that in that case, energy which is produced at the time of day when we would be most likely to be charging our plug-in typically has a high content of petroleum. So in that case, we're actually using petroleum to produce electricity, and we don't see an enormous advantage in terms of the displacement of petroleum by owning and operating a plug-in hybrid. Now, on the other hand, if we talk about greenhouse gas emissions, in that case, the benefit for a plug-in hybrid is not quite as obvious. For example, those of you living in California, or if we were to produce all of our electricity based on renewables. In those cases, we should see about, for example, a 50% reduction in greenhouse gas emissions. So those of you in California with Revolt, you're emitting about half the greenhouse gas emissions the rest of us are by operating your vehicle. So the take-home message here is actually that the source of the electricity is quite important. That electricity can come from coal, it can come from petroleum, or it can come from more benign sources like natural gas or renewables. That's the preferred method. Also, the extent of vehicle electrification also matters. If we can drive for a greater distance on a battery, we have a battery that allows us to travel more miles in all-electric mode, that should translate into more benefits as far as greenhouse gas emissions and petroleum consumption are concerned. So we've established that there are some real benefits to the electrification of the vehicle. The important questions now are, can we actually realize those benefits, and what sort of challenges lie in the way? So one of those relates to a situation that we're all familiar with. We're almost out of gas. We go to a gas station, we can fill up our tank in about 3 minutes and get 300 to 400 miles of driving in a conventional gasoline vehicle. So what happens now if I am in an EV and the battery's low? Well, I have to find a charging station, and in this case we're dealing with what's called a level 2 charging station, which means that it can charge up the batteries in this Chevy Volt in about 3 hours, which is not too bad. For comparison, if I were to charge this vehicle at home, it would take about 8 hours. And you can imagine that if I have a much bigger battery on my vehicle, if I have a full electric vehicle, and I'm charging at home, that could be a process which takes all day. So figuring out how to handle the charging problem, the inconvenience of charging, is something which we'll have to deal with in order to make electric vehicles more viable, to improve their commercialization. One thought is to maybe install more of these charging stations, for example, at places where people work. And so that's an infrastructure problem which I know that many municipalities are working on.
For this technology to really have a benefit to society, we've got to have everybody driving these vehicles, not just movie stars that are showing up at the Oscars. I'm really impressed every year at what sort of new electric vehicles show up at the top of the red carpet. But these are vehicles that I need to own, that parents need to own, take their kids to soccer. They need to be ubiquitous. And so we started talking about challenges a little bit already, and I mentioned this issue about the inconvenience of charging time. And that one's a little bit different because the other challenges that we'll mention have to do with technology hurdles. In particular, they relate to the battery. A lot of people, myself included, think that what happens with the battery is really what determines whether these vehicles will take off in the future. Other challenges that we're going to talk about, the first one is basically related to how much energy we can store in the battery per unit mass and per unit volume. And so sometimes people refer to this as the gravimetric energy density or the specific energy density when we're talking about energy per mass. Or they talk about just energy density, which refers to energy per unit volume. And so, a lot of people thought, not only the Department of Energy, but the automotive OEMs have thought about what sort of performance do we need to make these vehicles a reality. And they've come up with, maybe a dozen different targets for different aspects of the battery in its own right. Some of those targets include the gravimetric and volumetric energy densities. And to give you some perspective, and we'll look at this a little bit more in the lab later on, but what we need at this point is I'd say at least a doubling of energy per unit mass and per unit volume. And that doubling is something that we need to have essentially at the end of the life of the battery. So, people own their cars today for about 11 years on average. So the metric is that after 10 years of use, your battery should reach these DOE targets, which again are basically a doubling or more of where the technology is today. So we have a lot of work to do to figure out how to stick more energy into increasingly smaller and lighter spaces. So another challenge relates to cost. So again, if these vehicles are going to be democratic vehicles that a lot of people can own, should they choose to own them, they've got to come down in price. And I think we mentioned earlier that there have been some estimates that the 12 kilowatt hour battery we're using right now to drive the Volt costs about $10,000. And I think if you saw the vehicle I drive, you would know that the battery in this car is worth more than my personal vehicle. The goal is to reduce costs by about 80% compared to today's cost. So that would put us at about a target of about $125 per kilowatt hour. And right now we're a little bit over $600 per kilowatt hour. So there's energy, there's cost, we've talked about charging, and then the fourth issue, which we will also spend some time talking about later, is the robustness or lifetime of batteries. I think all of us have had the experience that you have a laptop, you have a cell phone, after maybe 2 or 3 years, the thing just doesn't operate the way you're accustomed to. It's maybe it holds a charge for half the time. And that's not really something we want to see in a vehicle. Like I mentioned, vehicles tend to have much longer lifetimes and upwards of a decade. So the goal is to have a battery, if we're specifically talking about an electric vehicle battery, something that we could cycle, say, 1,000 times and last for at least 10 years. And we're starting to get there, but this is, again, there's a number of ways batteries can go wrong. And we'll talk about some of those in a future segment.
So far we've been talking about energy storage and batteries in a rather abstract sense. Now let's start to talk a little more specifically about what a battery is, what its components are, and the mechanisms by which it functions. At some level, it's fair to describe a battery as a transducer. It's a device that converts chemical energy into electrical energy. And the way it does that is that it encapsulates two reactive compounds that when we put them in the same space and allow them to react will result in a change or a reduction in what we call the Gibbs free energy of the system. Now it's possible that that free energy could just be released as heat, but what's special about a battery is it manifests that energy change as a potential difference or a voltage across the terminals of the battery. So the connection between the chemistry of the reactions which are occurring in a battery and the voltage that we would measure across its terminals is nicely summarized by something called the Nernst equation. So in this case what we have is the change in free energy, and that is equal to minus N, where N is the number of moles of electrons that participate in the reaction, times F, which is Faraday's constant, and that's 96,500 coulombs per mole of electrons. And then finally that gets multiplied by the theoretical open circuit voltage. Let's see, that's F. So the nice thing about this equation is that this change in free energy, delta G, the energy change in the reaction, is tabulated for a number of different reactants. So in principle we can look up these values and make some prediction about what the theoretical voltage should be in a battery. And even in those cases where change in free energies aren't known, we have a really good technique that we'll talk about later based on atomistic calculations that allow us to calculate delta G values. Now we've already mentioned that one of the challenges associated with creating electrified vehicles is the relatively limited amount of energy we can store in batteries. And we talked about how important the energy per unit volume and the energy per unit mass are in determining how far we can drive in an electric mode. So a question is, how can we estimate those values? And to come up with a theoretical estimate is actually pretty easy. All we do is we would take that free energy change, which we talked about in the Nernst equation, and we divide that by either the mass or the volume of the reactive materials in the battery. So that's a starting point, and it gives us some feel for the potential of a battery. On the other hand, we also want to know practically what a real battery, how it could perform both in gravimetric and volumetric storage. To illustrate that, I have an example. We'll do a little experiment. In front of me is a battery module that we've taken from an electric scooter. And so if you can see in the front here, we've got some information about this battery, and I should say that this is a lithium-ion battery, and it uses for a cathode material lithium iron phosphate. So this is really a state-of-the-art battery in terms of the chemistry. So to get a practical estimate of the gravimetric and volumetric energy density in this guy, what we do is we would take the voltage, which is observed during discharge, and multiply it by the amount of charge which flows during that discharge process. Unfortunately, that information is included right here on the front. So if you can see this sticker, this is a 52-volt battery, and the amount of charge which flows, we're told, is 12,000 milliamp hours. So if I take those two and multiply them, that gives me the total energy stored in the battery, which is 624 watt hours. Okay, so that's the total energy. That's the numerator in our equation. Now to get the specific energy and the volumetric energy, well, the first thing we would do to get the specific energy is weigh this thing. So we've taken this downstairs and put it on a scale, and I think we got about 20.8 kilograms. That helps us with gravimetrics. So volumetrics, we're just going to measure the outer dimensions of this box, and so I get a width of about 21 centimeters. The height is close to maybe 8.2 centimeters, and then for a depth we have, looks like about 34.6 centimeters. So I have done some homework in advance. When I take those dimensions, convert them into a volume, what I get is a volumetric energy density of 102 watt hours per liter, and then the specific energy density is 61 watt hours per kilogram. So you might ask, well, how does that compare to targets for electric vehicle batteries? So below that I show what the Department of Energy is targeting for 2020 for EVs, and so they're looking for about, as far as specific energy is concerned, 250 watt hours per kilogram. So you can see where this battery is about a factor of 4 below that target. And then in volumetrics, about 500 watt hours per liter. So this battery is also about 5 values shy. So I'd say this is probably not a very highly optimized battery. For some batteries that we see on the road today, in automotive context, typically we're seeing, say, 100 watt hours or more per kilogram, and maybe close to 250 or so watt hours per liter. Okay, let's talk about lithium-ion batteries. These are what we call rechargeable or secondary batteries, and they really represent the state-of-the-art in rechargeable battery technology. So these are used in cell phones, they're used in your laptop, they're also used in basically any plug-in hybrid or battery electric vehicle you'll find on the road today. As far as the structure of a lithium-ion battery is concerned, there's really 3 major components. On the left you can see the anode. This is also known as the negative electrode. On the right is the cathode, known as the positive electrode, and in the center is the electrolyte. The job of the electrolyte is to allow for pretty fast lithium-ion transport between the anode and cathode and vice versa, and almost no electrical conductivity between the two. As far as materials are concerned, in the anode you should see planes, and that's because the anode typically is comprised of carbon-based material, so you see sheets of graphene, and the spheres in between them are lithium ions. So the lithium in the charged state of the battery will have a very high concentration in the anode, so you'd see lots of lithium between graphene sheets. On the other hand, if the battery was discharged, most of the lithium would reside in the cathode. And the cathode material typically is some sort of lithiated metal oxide. And when Sony introduced the first commercial lithium-ion battery back in '91, they were using lithium cobalt oxide, which is still used today. So let's now talk a little bit about how the discharge process works in these batteries. So we start, like I said, with a high concentration of lithium in the anode.
And during the course of discharge, an oxidation event occurs in the negative electrode, in the anode. So what happens here is that lithium atoms near the interface with the electrolyte become oxidized. So they lose an electron, which will go through the external circuit, and at the same time, the remaining lithium cation, the +1 atom which is left behind, enters into the electrolyte. Now at the same time, on the cathode, reduction event occurs. In this case, we've got a lithium ion entering into the lithiated metal oxide, and also the electron arriving from the external circuit arrives. So at the same time, we're oxidizing anode, we're reducing the cathode by inserting lithium into this lithiated metal oxide. And so basically that's a discharge cycle. Lithium on net moves from the anode to the cathode with the electrons going through the external circuit. And so you can envision this process as kind of like a migration of lithium across from anode to cathode, but then when you recharge the battery, the reverse process happens. So lithium ions would leave the cathode and move towards the anode, and an electron or a series of electrons flow through the external circuit. So to bring about that recharging process, we need to apply a voltage which is at least equal, but in an opposite sense to the voltage we measured during discharge. So overall, you can think about the discharge and the charge cycle in a lithium-ion battery as this rocking motion where lithium moves back and forth between the anode and cathode. And in fact, some people describe this battery as a rocking chair battery. Another bit of nomenclature is that we call this battery an intercalation battery, because what we're doing is intercalating lithium ions into either the anode or the cathode with with very little change in the structure of those anode and cathode materials. So essentially we're occupying vacancies within those materials without an enormous amount of swelling or structural change to the electrode materials. And basically that's it for lithium-ion batteries.
So thus far we've talked a little bit about the net energy which we can store in batteries, and we've characterized it in terms of volumetrics and gravimetrics. But we haven't yet said anything about power or power density. And power is important because when we drive, typically we have to accelerate for short periods of time, so getting that energy out quickly from a battery is quite important. We're here at the track to illustrate a trade-off between power and the net energy which can be stored in batteries. And the way to think about this is, imagine we've got someone that's going to run the 100-meter dash. That's an event where we run as fast as we can, exert or try to extract as much energy from our bodies as quickly as possible and get across that finish line. And usually at the end people are exhausted, right? So they've expended essentially all of their energy in a very short period of time because they released it so fast. Now compare that with what would happen in a marathon where we're running much slower. Maybe we're running for 3 hours or 5 hours. And so the rate of energy release is much slower, but the net energy release during that entire course of a marathon is much larger than what was expended during the 100 meters. So that's true for humans, and that trade-off is also true for batteries. So in front of me you can see what's called a Rigoni plot. And for some of you the name Rigoni may ring some bells. David Rigoni was a dean of the College of Engineering at one point. And so the Rigoni plot has a few nice features. It allows us to compare net energy. So on the y-axis we have plotted the watt-hours stored in a battery per kilogram, and on the x-axis is power density in terms of watts per kilogram. So with those two axes we can plot different battery chemistries. So you see a blue bar which represents a lead-acid battery, which is used for starters, lights, and ignition in your car. There's an orange bar which represents nickel metal hydride batteries, which are used in hybrid electric vehicles, and then there's a red bar which represents lithium-ion batteries. And so for all three of those batteries you can see this trade-off where if I pick a value on the x-axis that's far to the right, corresponding to a very large specific power, typically that results in, or in general that results in a smaller amount of net energy stored in the battery. So to operate the battery very quickly, we're going to be able to extract less energy from it, and that holds regardless of which of those three chemistries we're comparing. So another nice feature of this plot is that it allows us to also compare with other energy conversion devices. So for example, you'll see values for internal combustion engines and also for fuel cells. And finally, there's a value for ultracapacitors. And so these are the devices that have very high specific power, but trade that off for rather low amounts of energy, net energy stored. Finally, the other feature of the plot is that we can illustrate where our targets are for battery performance. And so you'll see stars that represent performance for, say, hybrid electric vehicles, plug-in hybrids, and for battery electric vehicles. The nickel metal hydride battery, which again is used commonly in hybrid electrics, satisfies the hybrid goals. Lithium-ion batteries will satisfy the plug-in hybrid goals, but to get to a pure EV, we need to have a battery which has better energy storage capabilities. You've probably all noticed that as time goes on, the runtime of our devices such as batteries and cell phones tend to get shorter and shorter. In a nutshell, this is the problem of battery degradation. Now, for things like cell phones and laptops, it's not really a huge problem because we tend to replace these devices pretty regularly. In fact, in my case, I get a new cell phone maybe once every 1 to 2 years. So you can see that this really isn't going to work for cars, however. Cars tend to last much longer, at least we expect them to. And nowadays, a typical car is on the road for maybe a decade or longer. So the problem of battery degradation in cars is really a major issue. I mean, we don't want to have to replace a very expensive battery, really ever. And if we have a significant reduction in range, then we're starting to lose out on some of the benefits associated with EVs, greenhouse gas emissions and reduced petroleum consumption. Because of this, an enormous effort is being devoted on the research and development side to try and understand and control how batteries degrade. And in this segment, we're going to talk a little bit about some of those mechanisms that are present in lithium-ion batteries. If I can make just one point about battery degradation, it would be that degradation mechanisms are complicated. While the symptoms are simple enough, power fade and capacity loss, these losses can be associated with multiple processes, and these processes can interact with one another. On top of that, it's hard experimentally to isolate these mechanisms and study them independently. So even though there are many different mechanisms, we don't have time to go through all of them. What we're going to do is focus on mechanisms that occur in the anode, because these are amongst the most important ones. So here we're showing a schematic of basically an anode in a lithium-ion battery. So you might recognize from our description of lithium-ion batteries the horizontal lines which represent the graphene planes in graphitic particles. The lithium in this case is represented by small spheres. Now to the right of the graphene sheets, you'll notice there's a yellow film. And this is a very important component of degradation. It's called the SEI, the solid electrolyte interface layer. And I would go so far as to say that understanding what's happening in the SEI is prerequisite to understanding almost anything about degradation in the anode. So the SEI forms typically during the first few charging cycles, and it's a result of a reaction between the electrolyte and the anode at the interface between those two materials. Now, it's not all bad news. Some aspects of the SEI are beneficial. In one case, the formation of the SEI has a protective effect, and it can minimize corrosion of the anode. On the other hand, once we form the SEI, the tendency for additional electrolyte to decompose into the SEI is minimized. The bad news is that there's many other negative assets or negative features associated with the SEI. The first one you can guesstimate just by noting that its formation arises from a reaction between the electrolyte and the anode. The SEI contains a fair amount of lithium, and lithium is an active material, so if it's tied up in the SEI, we're losing capacity. Also, we're essentially converting some of the liquid phase electrolyte into a solid phase, which means that it's not going to be useful for promoting ion transport between the anode and the cathode. And both of those effects can get worse as we increase the temperature. We tend to increase the rate of SEI formation at higher temperatures. The problem of power fade is also directly tied to the formation of the SEI. You can see that the SEI is getting a little bit thicker, and so as that thickness increases, the ability of lithium ions to easily migrate through the SEI goes down, and so we see a rise of internal impedance
which results in power fade. So that's not the whole story. Other bad things can still happen, and this would be associated with the formation of new SEI in the course of operating the battery. And these batteries, because we're intercalating lithium, there can be some small swelling in the carbon particles associated with that process. We can also insert lithium that's been bonded or interacting with solvent molecules. This is what we call co-intercalation of lithium and solvent. So that tends to exfoliate these graphene sheets, which would expose new parts of nascent carbon material, which could then further react with the electrolyte and generate new SEI. So SEI cracking followed by the formation of new SEI with some of that old SEI dissolving back into the electrolyte. These are all problems which at the end result in creation of new SEI over time. If we operate the battery at high rates and at low temperatures, lithium that's migrating through the SEI may in fact plate out as metallic lithium in the form of dendrites. So dendrites are sharp, spiky things that can pierce through the separator and result in a short circuit to the battery. So this is definitely a situation we want to avoid. That's a short rundown on some of the degradation mechanisms associated with anodes in lithium-ion batteries. I hope you can see that if we have any hope of controlling these processes, we need to understand them. And that's going to bring us to our next discussion, which will focus on techniques and tools for battery research and development.
Batteries have been around for a long time. In fact, the battery that you have in your car today, which controls the starter, the lights, and the ignition, that's a lead-acid chemistry which has been known for about 150 years. Even before then, around 1800, Alessandro Volta was the first to report a publicized battery. And there's even some evidence of batteries existing as far back as 200 BC. So with all that time for battery development, we need to ask the question, why has battery development been so slow? To give you an example, so if we take the creation of the lead-acid battery and look forward 130 years, which was the time span between that battery's introduction and when Sony introduced the first commercial lithium-ion battery in 1991, that span of time resulted in about a factor of 5 improvement in specific energy density. It's really not that impressive, especially when you contrast it with what Moore's law would have done in the same period of time. So Moore's law would have resulted in an improvement of about 10 to the 22. So clearly batteries have been moving a little bit slower than other technologies we're familiar with. The question is why, and one reason is that batteries are fairly complicated. They involve complex chemical reactions that involve simultaneous charge and mass transport. Also, a battery is a sealed device. We can't easily look inside to characterize what's happening. And on top of that, if we think about how to design a better battery, there's really lots of possibilities, lots of different materials one can consider for the anode, the cathode, the electrolyte. And in some sense, it's kind of like trying to find a needle in a haystack. So why are we so optimistic today? Well, is it suddenly that we're smarter? Well, in some sense, yeah, because we have access to much better tools. So we can characterize matter, we can manipulate synthesis of different materials, even down to the nanometer scale. We have tools for discovery, efficient discovery of new materials. So scientists and engineers can access this tool set, which spans not just experiments, but now includes computational modeling. We think to rapidly accelerate the rate, or to make battery discovery much more efficient and get over some of the obstacles we've talked about in a much shorter time frame. So like we talked about previously, one of the important aspects related to battery performance is degradation. And one part of degradation we haven't talked about too much, but is nevertheless important, is mechanical failure of, say, particles in the electrode. And this can occur as we insert or remove lithium. Stresses can be generated that result in fracture of those particles, and they become electrically inactive. So one thing would be nice is to follow that process at the atomic scale. And to do that is difficult because remember we said batteries are sealed systems. They involve liquid phases, which are typically not amenable to the high vacuum conditions one would typically use for a high resolution transmission electron microscopy experiment. So what scientists at Sandia National Labs have done have figured out a model system that allows them to follow these sorts of degradation processes in situ. And so to the left of me here you can see an example of the model system that Sandia came up with. It consists of an anode comprised of tin oxide nanowires. There is an ionic liquid electrolyte and
On the far right, there's a cathode consisting of lithium cobalt oxide, which is a conventional lithium-ion cathode material. So I say this is a model system, but it actually has some relevance to potential batteries of the future because there's a lot of interest in making electrode materials nano-sized. So for example, people have reported nanowire materials as battery electrodes already. And that's important, especially as we consider switching the electrode material. So in the case of conventional lithium-ion batteries, we talk about carbon-based materials. But if we could switch to silicon, for example, that would allow for much greater capacities of lithium to be stored in the anode. The problem with silicon is that when we insert lithium, there can be enormous volume changes, maybe a factor of 3 or 4, which results in cracking of those particles. And it's been shown that there's some hope that if we make those particles very small, nanoparticle sized or nanowire sized, then those effects might be reduced. So we would not have the sort of cracking we would see in the bulk phase. So with that bit of background, what the scientists at Sandia were able to show, I think is best illustrated in the bottom left panel of the slide. So there you'll see on the right basically an amorphous phase. It's a close-up image of the nanowire. So you notice it's a bit taller, a bit wider. That's because there's a volume change associated with the insertion of lithium. And what they're following is the recharging process, so the insertion of lithium into this tin oxide nanowire they're using in their model system. So to the left of that amorphous phase, you see maybe what looks like a tangle of spaghetti. That's where things really start to get interesting because that's a reaction front that involves the nucleation and emission, nucleation I'd say, and gliding of crystal defects called dislocations. So those can be observed directly in this experiment. And finally, to the far left of that, you see the crystalline tin oxide phase. So as time goes on and this battery is recharged, that reaction front moves from right to left, and essentially the entire wire could at some point become amorphous. You can see a zoom out of that effect of how this nanowire's morphology changes as a function of time, which is also a function of the amount of lithium stored in the wire. So you'll notice there's a small triangle, and that indicates the location of the reaction front. So to the right of that triangle, we have the amorphous lithiated phase, and to the left, there's the crystalline tin oxide phase. So as time goes on, that reaction front moves from right to left. And you can see that the wire starts to kink up, it starts to bend. So in addition to that widening we talked about, the lengthening of the wire is also a manifestation of this increase in volume. So in this case, when we factor in the widening and the lengthening of the wire, there's about a 250% increase in volume of this system. That's pretty phenomenal because tin oxide in bulk form is a very brittle material. And so what this shows that at nanoscale dimensions, we can convert a material that's typically brittle. Well, that material will exhibit a very ductile behavior. And so that gives us some hope for batteries of the future, not only because, like I said, we are interested in these nanoscale morphologies, but also now we're starting to develop the techniques that will allow us to look inside batteries and understand the mechanisms at a much greater level of detail. One approach to battery development that I think holds a lot of promise is based on computational modeling. It's called virtual high-throughput screening, and it has the potential to lead us to much better battery materials than could potentially be discovered by conventional methods. Now, to understand how this could work, I think it's helpful to draw an analogy with how drugs are discovered in the pharmaceutical industry. In that case, typically we have some sort of automated approach where potentially thousands of materials, thousands of compounds would be screened for their therapeutic efficacy. So that's a very expensive process. It's also rather time-consuming. So now imagine, what if you could do that on the computer? Thanks to Moore's law, in the past several decades, we've had enormous increases in computational power. So in principle, if we have an accurate way to predict materials' properties, we should be able to screen large numbers of candidate materials rather rapidly. In fact, I think much more rapidly than what we could do just using experiments alone. So how does that happen? Well, what I'm showing you on the screen here is an example of a crystal structure of a common cathode material, something which is known as lithium iron phosphate. And so this is an atomic scale image. The blue balls represent lithium atoms, the red atoms are oxygen, the gray represents phosphorus, and the orange is iron. So I show you this image because this represents the scale at which calculations today are typically conducted. These are known as first principles or density functional theory calculations.
And the goal is to find, using an alternative form of quantum mechanics called density functional theory, to find the electronic ground state of the system. If we can do that, then we can predict energies, we can predict free energies, we can even predict how fast lithium atoms could diffuse through these materials. For example, in the latter case, that would tell us what sort of rate capability we could expect from this sort of cathode material. An example of what virtual high-throughput screening can do for battery development is shown in this slide. This is some work that comes out of MIT, and what it plots is the theoretical specific energy of thousands of candidate cathode materials for use in a lithium-ion battery. So if we look at the y-axis, what's plotted here is the theoretical voltage, and along the x-axis is the theoretical capacity in milliamp hours per gram. And so you'll notice there's different colors in this plot. The blue represent oxide materials, the yellow is phosphates, red is borates, green silicates, and I guess aqua would be sulfates. And so out of all of these possibilities, the reason why this is helpful is because we can do, say, a thought experiment and say, I want to discover a new lithium-ion battery that has a capacity which is much greater than today's battery. So in principle, I could walk over here and say, let's draw a line at 300 milliamp hours per gram. And we want our battery to have a capacity greater than that. So everything to the left of that line I would throw away, which looks like it's maybe 95, 99% of the possible candidates here. So that's an enormous help, because now if I want to go back and do experiments, I don't have to try all of these possibilities. I know where to focus my effort. So let's push this a little bit farther and let's say, okay, I want something that's high capacity, but now I also want something that will work with today's electrolytes. So maybe we have to stay within a window of, I don't know, 3 to 4 volts. So now we're looking at a quadrant here above 300 just in this small space. And so we've come down to a subset of maybe 15 different candidates. So those can go to experiments, or we can even explore them a little bit further computationally. For example, we could ask how quickly could lithium ions diffuse through that compound? And that would be related to the power density, the power capabilities in those batteries. So as you can see, computation is really making some great inroads in helping us to screen through all of the possibilities and narrow them down to things which we have some hope of testing in a reasonable amount of time. So what does the battery of the future look like? Now that's a tough question to answer. But we know it should be smaller, should be lighter, should be less expensive, and should last longer. But other than that, it's really difficult to pinpoint a precise chemistry, mainly because there's just so many possibilities. In this segment, we're going to talk a little bit about some of those possibilities. And in the next segment, we're going to say give a little bit more detail about one of them that we're working on in my group. So to give you some sense of the overview or the phase space of possible battery architectures, we can start with lithium ion and say, well, we're going to make that system have higher energy density by replacing the electrode materials with things which have higher capacities for lithium. We could also swap out the electrolyte to something that could support operation at higher voltages. So voltage times capacity will give us a higher energy density. Related to that would be moving away from lithium to look at batteries that instead use multivalent cations, things like lithium or aluminum. So in this case, we would be getting a charge transfer of, say, 2 or 3 electrons per cation. A very different type of battery is an all-liquid battery. These are sometimes called flow batteries, where we've replaced our solid anodes and cathodes with a liquid phase analytes and catholites, which are some mixture of, well, in fact, they could be a slurry of particles that are conventionally found in a solid electrode with an electrolyte material. On the other extreme, there are all solid-state batteries. So this is like a lithium-ion battery, with the exception that we've replaced the nominally liquid electrolyte with a solid phase. And the challenge there is to come up with a solid phase which can transport lithium ions fast enough. The advantage would be that we could have a more robust battery, potentially a safer battery in all solid form. Another example, which is fairly near and dear to my heart, are what are called precipitation dissolution batteries. So an example of this, well, 2 examples of this class would be the so-called metal-air battery or the metal-sulfur battery. These batteries have amongst the highest potential specific energy densities of any battery, and that's why we're working on them in my group. So with that, you can see that there's lots of possibilities. Unfortunately, we can't go into all of those in any significant amount of detail. So what we're going to do is focus more in on the metal-air system, in particular the lithium-oxygen or lithium-air battery. Let's talk about some of the benefits associated with a lithium-air battery. On the slide here, you can see we've plotted
in blue bars the theoretical specific energy density of various different electrochemical couples. And in the far right of that plot, you can see a very tall bar which is associated with the specific energy of gasoline. So you see there's one other tall bar right next to it, and that is the gravimetric specific energy density for a lithium-oxygen couple. So it's actually much higher than basically all other common electrochemical couples, with the exception of hydrogen and oxygen. And it starts to approach the value of gasoline. So we're talking theoretically a value of about 11,000 watt-hours per kilogram. So that's pretty good, and that's part of the motivation for looking at the lithium-air system. So another question is practically what we can expect from this battery. And while we haven't built one of these, and as far as I know, no one has really done an extensive buildup of this system, there has been some analysis to project what a practical lithium-air system could achieve. And so what we know from that analysis is that on the gravimetric side, we can expect about a 300 to 400% improvement in gravimetric energy over a futuristic lithium-ion battery. So again, that's pretty amazing. Volumetrically, the payoff isn't quite as large. Again, compared to advanced lithium-ion, we're thinking about maybe a 30 to 60% improvement in volumetrics. So both of those sound pretty good. On the cost side, remember, of course, we want our future battery to be very low cost. There have been some projections that slate the lithium-oxygen system is coming in around $100 per kilowatt hour. So basically, those are the benefits associated with this chemistry. Let's talk a little bit now about how this battery would work. And so also on this slide, you can see the lithium-air cell showing both the charge and the discharge process. There's a magnification of the cathode. And what you see happening here is you see some gray. So this represents the cathode material, which is typically a porous carbon. You should also see a white blob, and this is meant to represent the reaction product. So this could be either lithium peroxide or a lithium oxygen phase, lithium oxide phase. In most cases, it's the peroxide which is observed, and it forms as a result of reacting lithium, which is dissolved in the electrolyte, with oxygen, which is also dissolved in the electrolyte, and with an electron that comes through the cathode. So the mass advantage of this system, as you can see, is based on the fact that one of the reactants, oxygen, does not have to be stored on board. We can flow it in as we need it, and that's represented by the oxygen molecule on the far right edge of the slide. So we call this system, this type of battery, a precipitation dissolution system, because in the course of operating the battery, we nucleate and grow one of these peroxide or oxide phases. And then when we recharge the battery, this phase has to decompose or dissolve back into the electrolyte. So that's, of course, very different from the sort of mechanism, the intercalation mechanism we talked about in a lithium-ion battery, where, for example, in the cathode we had a rigid host where we would intercalate lithium ions into existing vacancies in that material. So here we're making a new phase as we discharge the battery, and then that phase has to go away when we recharge. So that's a fundamentally different mechanism, and you can see that the creation and discharge, or creation and decomposition of this phase I would speculate it's going to be a slow process, and to some extent we see that in the rate capability or the power density of these batteries. So that's basically an allusion to one of the limitations of this system. Let's talk about some of the other limitations, some of the barriers to realizing these benefits in a real battery of the future. So I've already mentioned the power density issue. So you can see on the left, we've plotted the voltage as a function of charge state. And there's two lines here. The bottom curve represents the voltage we get out during discharge of the battery, around 2.7, 2.8 volts. And then when we go to recharge, you can see that we have to use a much greater potential, typically over 4 volts. So that hysteresis in the voltage capacity curve is basically telling us that we don't have a very efficient battery. For example, I'd have to put in maybe 100 units when I recharge the battery of energy, and I would get maybe 70 of those out during discharge. So about a 70% efficiency is typically one of the better lithium-air batteries at this point in time. And the main reason for this problem is the high potential during charging. We're not quite sure what's responsible at this point for that high potential. We call it an overpotential. There could be several mechanisms that lead to it. But that's one of the major areas of research right now, is trying to bring down that charging potential to sit almost right on top of the discharge potential. A second challenge is shown to the right, and that's capacity retention. So in this case, we're plotting the capacity as a function of cycle number. For early stages in the cycling process, maybe the first few cycles, we get a very high capacity, but then that falls off over time. And here again, there's some debate as to what's the mechanism responsible for this capacity loss. One possibility could be that when we form this peroxide or this oxide phase, that's an insulating film that prevents electron transport from occurring in the cathode. So basically the battery would shut down after that film gets beyond a certain critical thickness. Another possibility is that because we're dealing with a porous carbon cathode, a porous carbon support, those pores could fill up with the lithium peroxide and prevent or block any further reactions of lithium and oxygen. So like I said, there's some debate as to which mechanism, maybe some aspect of both are at play here, but solving the capacity, the efficiency problem, and there's a few others as well. We still have to deal with, for example, getting a pure source of oxygen on board the system. If we're flowing in air, we could have some nitrogen, we will have some nitrogen present. That could result in side reactions with lithium. Some water will be present. So do we really need a pure source of oxygen? And if so, how can we get that in a lightweight, efficient device? Also, to get maximum capacities, we'd like to have an anode, which is a monolith of lithium, so a pure metallic lithium anode. In that case, there are some challenges because we have to worry about dendrite formation. Like we talked about in the degradation discussion, we mentioned that lithium dendrites could form if we have a very thick SEI. And if we have a metallic lithium anode, the same process can occur, resulting in, say, a short circuit to the battery. So as you can see, there's some pretty big opportunities associated with metal air batteries. However, there's some big challenges. And so what we're trying to do now, even in my group, is trying to understand the mechanisms that are responsible for these limitations so that we can convert this battery into something that's, something that we play with at the lab scale on a lab bench right now, into something that would be a viable battery for electric transportation.
So as we bring this program to a close, I hope I've convinced you that there are some really very real benefits associated with the electrification of the automobile. We've talked about how electrification can reduce greenhouse gas emissions and can reduce our reliance on imported petroleum. To get there, what we really need is to solve the energy storage problem, and what that means is making batteries better. Batteries are the most expensive component of electric vehicles today, so reducing their costs means that more people will be able to afford these vehicles and will maximize their impact. Batteries also tend to suffer from poor robustness. They don't last as long as we'd like them to. And so you can see there'd be some real costs associated with having to replace a battery very often. Finally, if we can make batteries have higher energy densities, we can expect to travel greater distances in all-electric mode, which should further reduce greenhouse gas emissions and our reliance on petroleum. So coming up with a battery that's lighter, smaller, less expensive, lasts longer, really is a grand challenge. Fortunately, we've got some of the best minds, best engineers and scientists working on this problem, and they've got access to tools which a decade ago were unprecedented. We can characterize materials now at the atomic scale, and we can use high-performance computing to make predictions about which materials ought to lead to the best batteries. So looking to the future, it's hard to make predictions, but I'm betting that we're going to have a breakthrough, and soon we will see much better battery technology.